is a TA. Is there a TA for the? Yeah, there is a TA.
There is a TA, but I think Godowski does his own stuff with
Okay.
with the exams.
Because I know TA for CS class and he gets all the answers.
You can't say that. We're live. All right, what's up?
Yay.
Not much, how are you? What? I said, not much, how are you?
Okay, good. How's life treating you?
Pretty good. There's a tea unit. You know, I don't know if you sell the posters on the street. The tea, her tea, on her floor.
Is this a stress thing for finals?
Yeah.
The de-stressing thing.
Tea for de-stressing.
Yeah, why not?
Coffee.
Okay, so
I'm not stressed anymore. Coffee doesn't help. What's up?
So Orgo was fucking with me so hard. I have no idea what's going on. This is like I haven't done anything.
Since when?
Okay, I'll tell you since we started to add some stuff to circuits, more of like this thingy and then the
squiggly thingy.
like when we started to add some stuff to the circuits, I just like okay.
Oh, the AC circuits?
AC, LRC, that stuff, yeah. Like, can we just go over that? I don't know.
AC and LCs. AC and LC, how does it start?
Yeah, like, okay, so you know how usually they give a circuit and then they ask a bunch of questions. So at time 0, and then if something is closed, if something is open, like, can we like do something like?
You remember the LC circuits with just an inductor? Remember the not LC, the LR?
Yeah, can we do that as well?
This and the batteries.
Okay, so
Remember that?
what's not here?
Okay, so what's different about inductor? Well, capacitors, if you remember a capacitor, when a capacitor was, okay, so yeah, this. Just quickly try to go very quickly. In this case, a capacitor, you have a switch here.
Yes.
And when you close the switch, what happens to the capacitor? So at t equals, let's say at t equals 0.
Okay, hold on. What happens when the switch is open? Oh, when the
we're assuming that it's still open and nothing happened yet. We're going to reopen it after a while. So let's assume first it's been open for a long time.
Okay.
Okay?
Yes.
And then at t equals 0, you close it.
Are the capacitors discharged?
Yeah, we're assuming that it's
Okay.
uncharged.
So when we close it, they start to charge?
So when we close it, it starts to charge. At first it acts like a wire, right?
At time 0.
T equals 0, it's going to be a wire.
Yes. So there's only resistor.
So there's only the resistor. So the capacitor. So
Wait, this
capacitor
one is a battery
is
and the other one is capacitor.
wire. Yeah, this is a capacitor. This is a capacitor. This is a battery. And here we're just going to do the same circuit but with an inductor. You should see the difference. And we're going to say at t equals 0, we're closing it. Okay?
Mm-hmm.
The capacitor is completely uncharged. At t equals 0, the capacitor is completely uncharged. So it lets all the current that passes, it lets all the current pass through it. So it's a wire. Here's the inductor. At t equals 0, the inductor works based on Lenz's law. When you have flux, so an inductor is basically a wire that's coiled up, right? When you have current that goes through a wire, there's going to be a magnetic field. And according to Lenz's law and Faraday's law, you remember?
Yeah, it doesn't want any changes.
Right, it doesn't want any changes. That's right. It doesn't want any changes. So when you close a circuit, there's going to be current flowing through. The inductor doesn't want that current to flow through. So it's going to create a back EMF.
Yeah.
Which is going to stop all the current. Therefore, open circuit at time equals 0.
When this is closed.
Yes, at t equals 0, right when it's closed. Okay.
What means open circuit again?
Open circuit means that
There's no current.
yeah, there's no current, so you just take it out.
But there's current in.
Yeah, there's current here. We're only talking about this branch.
Yeah. Okay.
So that. And when at t is equal to infinity,
Okay.
what happened here?
Okay. So capacitor is like fully charged, so there's no more current.
Right, so open circuit.
Okay.
And here, at first, right when you close the switch, there's a huge change in current. Current went from 0 to infinity, or 0 to a big value. So the capacitor, the inductor, saw that huge change and wanted to stop it. But after a while, the change is just going to decrease. So the graph looks.
Right. It goes like this.
The graph looks actually like. Well, after the change, it looks like that.
Oh. Why?
Through the inductor.
Why?
At t equals 0, it's open circuit.
It's graph of what to what? Time to.
Wait, it's current and current versus time.
What about voltage and time?
Of the inductor.
Yeah.
Because at t equals 0, its voltage is going to be, since there's no current here, all the current is flowing through here, right?
Right.
So its voltage is going to be the same as the voltage of the capacitor.
Okay.
After an infinite, so here at t equals infinity, all the current is going to be flowing through the inductor, right? So the voltage across it is going to be the same as the voltage across the resistor. But since there's no current flowing through the resistor, there's no voltage across it. So its voltage is 0. So here it's 0, here it's max. So it looks like that.
Yes.
That's the t. So here at t equals infinity, L is short.
Like, I don't understand when you guys say open circuit, short circuit.
Short circuit means, when you short a battery, for example, you have a battery, a 9-volt battery or whatever. You short it by connecting these two terminals to a wire. That's short circuiting. Anything in the world, when you take its two terminals and connect it to each other, that's short circuiting. So when we say short circuiting this, we're just taking two wires and short circuit. It's just two wires connected to each other. There's no elements between it. We're assuming.
But it's like also like a wire.
Yeah.
So can we say it's the same as?
Yeah, it's just a wire.
Okay.
Open circuit, as in it's literally not connected. There is no circuit.
Yeah. Okay.
Open.
Okay.
Sure. Wire instead of short circuit. And the same thing we did with the capacitor, we do with the inductor. But no, for example, we're asked about, let's do the same circuit actually. I'm just going to erase this and this. We're not going to do capacitors because we already did them.
But they will be on the final.
Yeah, they don't. So let's say we want so after you open this circuit, actually let's go back to here.
Yeah.
When this is completely charged, close it, completely charged, and then after time t equals infinity, you reopen this. What happens when you reopen it? This entire circuit is gone, right? We don't care about this part of the circuit.
Yes, so we only have
care about this. Positive current was flowing from here to here, so this is positive and this is negative, right? And we're going to have a current going right here, right? And what stayed the same about the capacitor? The voltage across it, right? Voltage across the capacitor right before, t equals infinity, right before we open the switch, the voltage across the capacitor is exactly the same as the voltage right after you open the switch. Remember that? The voltage of the capacitor stays the same, right?
All the time?
Well, in this case. Usually, the charge stays the same in the capacitor, right? And since, in this case, you didn't change the capacitance, therefore the voltage stays the same. Because Q is equal to CD. Q stays the same. As long as C doesn't change, V also stays the same.
He's just reading his book.
Which book is that?
1984.
What?
1984. Orwell. What?
Never heard of it.
Oh. George Orwell? Have you heard this for the author? No.
I'm not close to
Alright.
Yeah, okay. So the voltage stayed the same before and after you open the switch. Here, the current stayed the same.
Oh,
current for the
the
inductor stays the
same,
same,
right before we open?
Right before we open, right after we open. Because remember, the inductor doesn't want anything to change. Nothing. Doing death threats. The inductor. So remember, the inductor doesn't want anything to change, right? So right after you open the switch, the inductor wants the same current flowing through it.
Yes.
Therefore, the current is going to stay the same, and then it's going to decrease exponentially. So I mean, the graph looks something like that. The current. Here we open the switch. Sorry, we close the switch. This is t equals 0. T equals 0. Close. And this is t equals infinity. We open. The current is going to decrease like that. But
Okay.
right to the right of this graph and to the left of this graph, the current's the same.
After we open
Yeah.
that stuff. Okay.
The current's the same. So we know the current is going to stay the same here, right? We're going to ignore this part of the circuit, right? We're ignoring this part because we're opening the switch.
Yes.
Open circuit.
Yes.
The same current that was flowing through this inductor is going to flow in the circuit,
Okay.
right? So the current is going to stay the same.
Does it matter in which direction in this case?
It's going to always go in the same direction as it was before. In this case, the current was going like this,
Okay.
and when you open it, it's going to still go like this.
But in this
It was different because positive charges were moving from here to here,
Mhm.
and we define current as positive charge flow. So positive charges were moving from here to here. When you disconnect this part, positive charges are going to exit where they were stored. They were stored here, so positive charges are going to move like that.
Okay.
Yeah.
Yes. Okay.
Your current keeps on moving the same direction.
Okay.
Okay?
Mhm.
And the voltage across it can be whatever. The voltage across it can jump. It's going to jump from 0 maybe to 200 volts across the inductor. Because it has to raise itself to whatever it needs to be to keep current flowing, to keep the same current flowing through it.
Mhm.
This right, I mean, look at this here. So the voltage graph. So the voltage graph starts out at 2 up there. This is the at t equals 0 when you close the switch. Voltage decreases until it's going to be a short circuit here, right?
Mhm.
Or just a wire. Then when you open the switch, the voltage is going to raise itself to whatever it has to be to keep the current the same. It's going to decrease again. Okay? The same thing actually with the current through the capacitor there. Because the current through the capacitor starts out like that. This is I versus T. Because at time t equals 0, the current through the capacitor is maximum, right? It's just a what? Oops.
No.
Did something wrong.
Mm-hmm.
Because at time t equals 0, the current through the capacitor is maximum, then it decreases. Oops. Okay. And then we open the switch, current through the capacitor.
So are they the same, the graphs?
Yeah, the graphs are pretty much the same.
That's false. That's false.
That's voltage, this is current though.
So this is not correct?
What is it? This one? No, this is current through the inductor. This is
Okay.
voltage of inductor. That's
Yeah.
current through the capacitor.
Okay.
Yeah.
Okay.
Right? Because at time t equals 0, this maximum current decreases with time. Then you open the switch, and it's going to flow again and decrease. It's all exponential. So yeah. And this doesn't have to be the same as this. And this also doesn't have to be the same as this. The only thing that's continuous here is the voltage. The only thing that's continuous here is the current. Current has to stay the same before and after. Voltage has to stay the same before and after. Voltage can't jump in the capacitor. Current can't jump into the inductor. They're kind of like opposites of each other. But yeah, that's basically this. The RL circuits. And they can ask you a bunch of stuff. The same thing that they asked. I'm just going to take the same circuit that we have here. They can ask a bunch of stuff.
Yeah.
And we solve it the same way, but opposite. I mean, 9 volts, 3 volt, but 3 ohms, 6 ohms, and some L. We don't care about L. And we're asked about, say, we have the switch closes at t equals 0. Okay, switch closes at t equals 0, and at t equals infinity, we open the switch. What is voltage? Voltage of inductor after opening. So the first thing we want to do is find the current through the inductor right before we open, right?
It's gonna be
Current through the inductor right before we open is going to be, so current at t equals infinity. What's going to happen at t equals infinity? The inductor?
Wait. Okay, hold on. Okay, so this is closed. Yes.
Closed? Yeah.
And then there is current. Okay, and then we open it. So there's no current on that side.
Right, but before that, to know how much voltage we have.
Right, okay. So current right before we open is the same
as
as
the current right after we open. Yeah.
Yes.
Okay.
So we can find the current when the switch was closed at t equals infinity,
Yeah.
and it's going to be the same as.
How do we find that current? What happens at t equals infinity? What happens in the inductor?
Well, the current's just going.
Where?
Like this.
Yeah, like that, right? So there's nothing here, right? So all the current flows like that, right?
Can you say why there's nothing in between?
Because at t equals infinity, the inductor is a short circuit or a wire, right?
Oh, right. That's
Right.
what he was telling to me. That if the current prefers to go
In the
in
least
the yes.
path of the
Okay,
least
got
resistance.
it. He's been trying to teach me that stuff.
Okay. So the current goes in the path of least resistance.
Yes.
And it's going to go in this direction. So the current is, there's only one resistance in this.
So it's 3
path.
times 9.
I know.
9 over 3 is sure. I'm
Is
sorry.
equal to IR.
Yeah, whatever.
Okay, which is equal to 3 amps. So that's the current. So I'm just going to draw the graph again. Graph starts out as maximum current at D. That's an ugly graph. Max. Okay, so it starts out as minimum, right? Because there's no, yeah. So here, this is I, this is T of the inductor. This is 3 amps, right? And here's where the switch changes. This is, we're assuming this is t equals infinity, which is, this is completely wrong mathematically, but forgive me. So this is 3 amps. That's the maximum it reaches, and then it starts to decrease right after you open it. But the second you open it, this is the circuit. Wow. So right after you open it, I didn't know I could do that. So this is not a short circuit, this is in there again. So when you open it, this is going to be ignored.
Yes. Yes. And the current still will be 3 amps.
What direction?
It's still like that.
That's the direction of the current, right? And the current is still going to be 3 amps. But the voltage across the inductor is going to be the same as the voltage across the resistor, right? Right? Right?
Yeah.
Because they're in parallel.
Yes.
This is just a wire, so the voltage from here to here is the same as the voltage from here to here. Right? The voltage across the resistor would be
24.
equal to I, right? No, 18. 18? 6 cents here, 18. Oh yeah, wait, I get the point. But notice that, remember that if you have a resistor that looks like this, and you know that the current is flowing this direction, this is positive, this is negative, right? Because across a resistor, current always flows from positive to negative.
Yeah.
So here, this is positive, and this is negative.
Okay.
Okay?
Yeah.
That means the voltage from here to here, positive negative, is equal to 18. If they ask about that, it would be negative 18. Okay?
I don't get this part. Like, okay, so so there's plus there where 9 volts, right? There's plus, yes. And this is going this way.
Across the battery, it's the other way around. I mean, because plus means high voltage.
Yes, and you said that the current is flowing
From high voltage to low voltage.
Yes, so
From high voltage to low voltage.
But why is there minus over there?
Oh, this is after. This is before you would have. This is before you reopen the switch. It's a positive, negative, positive, negative. That's how the current flows, and then no more current flows. then we open the switch, this entire circuit is ignored.
Yes, and then it's going.
The inductor is the only thing that's controlling the current now.
Yes.
And the inductor wants the current to flow in that direction.
Yes.
Since the current is flowing in that direction, that means
okay,
this is higher voltage than
yes,
this.
Yes, I get it.
Okay?
Yes, yes.
Okay. So this is higher than this, and that means the voltage of this is higher than that.
Because we are going that way.
So if they ask about this positive, negative, that's going to be negative
No
18.
problem.
Negative.
Volts, okay.
Cool. Okay. What's next?
AC.
AC?
LRC.
RLC?
LRC first.
Is that the one without a source? Wow. I don't know.
Wait, the LRC circuit?
Yeah.
Do you have it out there or no?
Are those the ones
I
without?
have it. I got it. Okay. LRC. There. Oh, something's wrong over there. Okay, LRC. Those stuff. That kind of
Actually, yeah, that's a problem.
That kind of stuff.
One of the column?
No, it's not. I know how to do that one.
Sure you do.
I did that one.
Can I see the other ones that they talk about? That's a very
Okay.
general idea.
That one's LC.
It's just, the others are all LC.
Okay, LC or LC,
It's not
okay, no
blue.
source, that's a point. Oh, there's a source. Well, we'll do one source, no source.
Yeah. Seriously?
So in one of them, I mean, we have something like that, right?
This is not number 6.
Let's assume this is charged, completely charged. At t equals 0, C is charged, so maximum, and the inductor has no current, okay? And if you leave everything the way it is, so
Is there no battery?
in this case, no, there's no battery. We're just trying to introduce a concept. So the entire point of this is that, let's say you have a capacitor here, just connected across a wire. Let's say the capacitor is charged. What's going to happen when you connect this wire? Charge is just going to flow like this, right?
Charge.
Charge. Which current?
Oh, wow.
Okay. Current or charge is going to flow like this, right?
Yeah.
From the positive to the negative. They're just going to want to go back to where the original place was.
Yeah, okay.
Now, if you add an inductor like this, put an inductor instead. Charge or current, and this is charged, this is completely uncharged. Current or charge is going to want to move in this direction, right?
Yes.
But since there's an inductor in the way, the inductor tries to resist the change, right?
Sure,
Yeah?
Yeah. I mean, it does, but
Yeah. So at first you have charge coming out of here. Inductor is going to try to resist this charge.
Yeah.
Okay. When the capacitor is discharging at its maximum rate, that's when the current through the inductor is at its minimum rate. So, I want to do it in a really simple way. I don't want to get into the out of phase 190 degrees concept, so I'm not going to until we get to phasers.
I think I actually understand phasers.
Oh, you do? Okay. Phasers are easy. Kind of. These are workers. So what does I want to say here?
What's the question?
I'm just going to.
Is that what you're trying to come up with?
I'm just trying to explain. No, it's not it. I didn't come up with anything. Okay, let's take the other way around. Let's say we have current here. Let's say we have current flowing through the circuit.
Okay, I understand that when the current goes this way, the inductor wants to resist it. But
Yes.
what? So what?
So when the inductor is resisting current, what is happening is the inductor is storing energy. Magnetic energy. Magnetic energy is stored in the form of moving electrons.
Mm-hmm.
So electrons are literally moving the wire.
Mm-hmm.
And then we're going to get into the fact that everything has an inductance. So that's why I'm trying not to go there. So if you have let's say we have positive charges here, negative charges here. What's going to happen is the positive charges will want to go back there, but the inductor is going to resist that change, right? The inductor is going to resist that change, and as current is flowing out of this side, it's going to go into the inductor. It's going to be stored in the inductor in the form of current.
Okay.
So the charges are going to be stored in the form of current in the circuit.
Kind of charges.
Here, in this case, positive charges and negative charges are going to go in that direction, right?
Okay.
So after a while, the capacitor is going to become uncharged. Okay.
Yes.
The capacitor is going to become uncharged because it emptied all its charge out. The inductor is going to become a short
Don't
circuit.
they? Oh, okay. Yeah.
Inductor is going to become a short circuit.
Mm-hmm.
So, right in this time frame, right in this picture, you have maximum current flowing through your circuit and minimum charge on the capacitor. Remember, positive charges were moving from here to here. It's uncharged, so I'm gonna. Positive charges are moving from here to here, and negative charges are moving the opposite way around. So now this plate becomes positively charged. This negative charge is moving that direction. This plate becomes negatively charged.
Okay.
Okay. And when that happens, there's no current in your circuit. When they reach maximum positive charges here again, maximum negative charges here again, you have no current in your circuit. So you're back to an opposite situation as we were before. So you have that going on.
Mm-hmm. Okay.
And it continues to oscillate. So it's like energy is being traded between the capacitor and inductor. Because remember, they're just storage elements. They don't.
Is it just going all?
Yeah, it's just
all
going.
the time?
It's just going back and forth and back and forth and back and forth.
Okay, so
So
there
that's
is
what-
maximum current and minimum current.
Yes, there's maximum current and minimum current. It looks something like this.
Okay.
Sine wave oscillations. This spot, for example, this is, you could say
So when there is maximum charge,
there's maximum charge.
it means this is the first picture you showed.
Yes. If we're assuming, yes, you can say that. We can also draw, to be more specific, we can say this is the voltage. Okay, because Q is equal to CV, maximum charge corresponds to maximum voltage.
Yes.
But because voltage gives us a direction, we can say this is the voltage. So this picture corresponds to this.
Mm-hmm.
And in that case, we have, I'm going to say I is in green. We have no current, right? Let's define the current in this direction. When the capacitor is completely uncharged, you have maximum current flowing through your circuit. It corresponds to this max.
Mm-hmm.
And after a while, you're going to have the voltage reversed, or the charge reversed. So you're going to be here. And at that moment, you're going to have no current in your circuit. And so they're going to oscillate like that. It's ugly and red. But yeah, you get the point. The peak corresponds to the minimum. And the zero corresponds to it.
Okay.
I say minimum, I mean magnitude minimal. So, I mean distance minimal. That's just direction, it doesn't really matter. But yeah, this is why when you draw a phasor diagram, because, I mean, look at it this way. If this is your sine function, this angle is pi over 2. Because this entire thing is 2 pi, and this is 4th of it. This is pi over 2. That's why when you draw your phasor diagram, you have current here, and for example, DC here. And you know this is 90 degrees. That's why we say it's 90 degrees out of phase. It's pi over 2. 90 degrees. It's 90 degrees out of phase. Time-wise, takes it 90 degrees, or 4th of a cycle, to get to what the other thing got to. And when you add a resistor, so I'm just going to draw a graph of one of them. I'm just going to draw a graph of the current, for example, like that, okay, for the original circuit. Now, when you add a resistor, you have the original circuit. Remember, these elements on their own, they don't consume power, right? They just store power and then deliver it after another cycle. The resistor consumes power. So it dissipates power in the form of heat. takes in current, resists it, and gets hotter. So there's loss of power. That means your energy is not conserved. So the current is going to be decreasing over time. Okay? That's what the resistor does. It dampens the waves. And, well, let's see. So if you add a source, that is, and there's this, okay, so when they're oscillating like that, the frequency of the oscillations is called the natural frequency, because that's the frequency that they naturally want to oscillate at. That's a frequency where they just want to move, where they're going to be 90 degrees out of phase. Okay. So if we put an AC source is just a voltage source.
Yeah.
Remember.
Why is it so different from the?
What do you mean so different?
Why do we have to put this thing instead of these?
Because, well, the actual symbol for the DC source is, well, this is sources in general, I guess, so we can say that we use this symbol for DC sources because it's batteries that are usually DC.
Okay.
And DC means, so if you have voltage versus time, this is the graph of a DC voltage. It's just constant with time. It doesn't change. And AC is going to alternate between negative and positive. This is just one form. The sine wave or cosine wave is just one. It just alternates between positive and negative. It just changes directions. So another another form of AC is,
Okay.
the important thing about AC is that it changes direction.
Yeah.
It alternates. And technically also, if it doesn't change direction, it also, as long as it's not constant, they also call it AC. This is also AC. AC with a DC offset. But let's not get into that. But yeah, we'll just focus on the changes direction. That in half of the cycle it's positive. So it's positive, it's a positive. The other half it's negative. So if we...
It's the voltage, right?
Yes, the voltage. We're just talking about voltage sources here. So. That's that.
Okay.
So, if we manage to put a DC source that has the exact same frequency as the oscillations would have had if there wasn't one, which is, remember, we said that the frequency at which these oscillate at, if they were like this, that's a natural frequency, right? Nothing is really impeding anything. They're at the same time, they're strengthening each other, right? This is maximum, this is minimum, this is minimum, this is maximum. If we manage to put a voltage source that's in the same frequency as these and in the same phase, we're also going to have the same thing. Nothing is impeding anything, and it's all strengthening itself. In that case, that's when you have something called resonance frequency. At resonance frequency, I think resonance was actually after phase restraint.
Yeah, it was. It was just like not the last lecture, but the lecture before.
No, that was waves.
Hmm?
That was electromagnetic waves.
Yeah.
Actual lectures on electromagnetic waves already.
Oh, really? I mean, I skipped the last one.
I like how I know what's going on in your class. That's always
I think
good.
the last two lectures were about waves.
Yeah.
Okay, then the lecture before that.
Let's see.
Whatever.
But anyway, yeah, if the source has the same frequency, so everything in the system doesn't really oscillate, but these two are going to be oscillating at the same frequency, so nothing's going to be impeding it.
Okay, so when they're in the same frequency, then they're at resonance.
They're at resonance, yes.
Okay.
And I mean, the equation for resonance, what is it? 1 over root LC, I think. Right? Omega naught resonance frequency. It's 1 over root LC. So it depends on L and C. You know that for a fact. It depends on L and C.
Okay.
And at that point, when resonance happens, since these are working, these are pushing and pulling.
Whatever.
These are, I mean, getting their highs and lows. And at the same time, this is getting its high and low. These don't really affect your circuit. It's not really impeding anything. The capacitor and the inductor are working with the circuit.
Yeah.
So you can pretend that they don't even exist at resonance. So the only thing that's happening is, and in the phasor diagram, this looks like, remember in the phasor diagram, the length of this vector phasor is the same as the length of that. Okay? So they cancel each other out.
Oh,
That's in the phasor diagram. When omega is equal to omega not resonance, sure.
Yeah.
So the voltage, this is the LEC, and the black one is VR. And this is the VEMF.
Is VR also equal to VC and VL?
No.
No. Okay.
In that case, VR would be equal to the voltage of the source.
Yeah. Okay.
Because there is no voltage across. I mean, the voltage across these cancels out. It's negative with the other voltage. I mean, look, since this cancels out with this, and remember that this VEMF has to be the sum of all of them. These are 0 together. That means this equals this. VR is equal to VEMF.
Okay.
Okay?
At the.
At resonance, yes.
Okay.
Are you taking linear algebra? Are you taking linear algebra? It's sad.
Here, we don't go over much.
Really?
Hardly anything. We can go way much more, but we go over this much in matrices. We could hardly talk about transformations of matrices. I don't know. It's all the linear equations of matrices. But yeah.
Wait, really? Is that like the whole class?
No, a good portion of it is nice equation. But the MIT course is good though.
Yeah, it is. I looked at it already.
Yeah, it's pretty good. The professor is amazing, actually. Gilbert. See, the thing is, their courses that, sorry. No, the thing about their courses is that their professors usually write the books. So the professor like knows exactly what's in the book, like referencing it from the top of his head. Right. But anyway, yeah. What's next? What's the next topic?
Yeah.
Yeah. What?
AC.
AC. AC. What AC? What is? Like phasers AC?
Yeah.
Yeah, you know the phasers? Is there something before phasers related to AC?
So we did the we did the LC here. AC circuit. Okay, this side, and then that stuff.
I mean, they're all pretty much the same.
Yeah, stuff. Okay, but there's something else. There is AC circuits, resonance, and power. Okay, this, no, power.
And we'll just say, just a point where, I mean,
Yeah.
we said that this is the AC wave. It's described as a function of cosine. This is Vmax, cosine or sine. So sine or cosine of some frequency. This is the frequency it oscillates at, plus some phase angle.
Yeah.
Phase angle is how much it's shifted, right or left. So positive phase is going to be shifted to the left. Like that. Sine starts at 0. Something like that. Right, this is Vmax.
Okay.
And that's just the description of the source.
Yeah, that's just that thing.
Yeah, just you can go over the equation.
And then the electromagnetic waves, there's.
Yeah, electromagnetic waves.
Yeah. Yeah, I skipped the last lecture. I don't know what it was there. It's
It's
properties.
just more about waves, honestly.
Or not waves. Oh, for the homework that was today, I had question why. Okay, so we got it, but like Okay, so you know how if you put the answer and it says, oh, so the sign is not correct, so you just put a negative sign and it's correct answer. But like, why is it something negative?
Is S the Z component? This one?
Yeah, actually that one in particular.
What is S the Z
This
component?
one in particular.
So Z the Z component of the vector at x equals 0, y equals 0, and t equals 0. Do they tell you what direction everything's going?
Yeah, but I have like problems with doing this.
The E cross B thing?
Okay,
It's E cross B gives you S, right?
yes, okay, what is it again?
E cross B gives you S.
Ish. Okay, E cross B equals S. Yes. So, which one's cross? So this one cross this one gives
E
you
cross
that.
B gives you S. Yeah.
E cross B is that. Okay. So, it says that I and J hat are in positive X and Y directions.
I and J.
There's three. Like,
Oh, okay. The X is equal to 1. The Y is equal to 4.9. X, Y, Z.
yes.
X is equal to 1, Y is equal to 4.9, so it's going to look something like magnetic field is blue, right? This is B.
Okay.
Okay, and what do we know about E? Do we know anything about E?
No, I think that's what they're asking.
I mean, I found E.
Oh, well, we know the direction of S already.
How?
KZ plus omega T. So
What?
it's going to minus negative Z.
KZ plus omega T equals
Okay.
what?
No, that's
Actually, yeah, that's something.
That's what everyone's confused about usually. Well, what usually everyone's confused about is what the hell is a wave, because no one really ever explained it. But that's also one thing that everyone's confused. What's a wave? No waves.
It's like
So that's the answer. Oh, it's just a squiggly sign. What's a sound wave or a ocean wave? Water wave. Whatever.
Oscillation.
Something oscillation, right? It's just a disturbance. It's a disturbance in some medium, right? So in water, it's just you disturb the water, and those oscillations or disturbances travel through the water. With sound, it's just a disturbance that travels through the air. What about an electromagnetic wave? We say it travels through vacuum. How does that actually happen? Water is the medium. Vacuum is not medium, right? It's nothing empty. What's the medium? An electromagnetic wave. It's an oscillation of something, right? What's that thing? We don't have to get that complicated. We don't have to go into quantum mechanics.
Oscillation of waves.
So electromagnetic wave doesn't actually travel through vacuum. I mean, syntaxically, it's incorrect to say it travels through vacuum. The wave travels through the electric and magnetic field. The electric field travels through vacuum. So the electromagnetic wave is just an oscillation in the electric field. And when we draw the components like that, that's just the electric field oscillating. Right? That's just the electric field changing directions. Why is it oscillating? Because, for example, how it starts. You remember that the change in electric field creates a magnetic field, right? And a change in magnetic field creates an electric field because of Maxwell's equations. Where have you got that? We'll ask him. So, if you have an electron, proton, make it easier, it's going to have an electric field going in that direction, right? Now the electric field travels at the speed of light. I mean, light is an electromagnetic wave, or makes sense. That means the electric field is not instant. Let's say you don't have an electron, and after some time, really small time, you place an electron there. The electric field there is still going to be zero. But after a small instance, because the electric field is actually traveling, it's being created, the electric field there is not going to be zero anymore. There's going to be electric field that this proton is going to be affecting electric field. The electric field, I mean, it moves. It has a speed. It's not instant. So let's say you place an electron here, it creates an electric field, right? Now we move this electron here. This is the new position of the electron. or a proton in this case. Okay? I'll leave the old fields. I'm going to draw them a bit longer. But after we moved it, and there's also something happening in between, but I'm just going to simplify things. We're just going to talk about here and here. When we moved it here, the new electric field lines look something like this. Well, actually, let's say we're still at a time interval where the electric field lines have only reached this far. Okay? So the radius that they've reached so far is this much. So in this area outside, it's still being affected by the electric field that was there because it's traveling. Okay? So it's still like something that's traveling. When we moved it, that same thing is now traveling outside of here, but here is still being affected by the original one. That difference in the direction, we have another one there, but yeah, let's talk about these. That difference in the direction is the pulse of the electric field that's traveling. When we do that, electric and magnetic field, that difference, that's a change in electric field. That's the change that creates the change in the magnetic field. So the change in electric field creates a change in magnetic field, which creates an electric field, except that it's okay. That's how the change in electric field is created, by motion of electrons. That's what when you have like an antenna or something, they just have electrons moving around. Switching positions around it. That's creating an electromagnetic field. Electromagnetic wave, sorry. Which oscillates and travels through distance. Yeah. So that's what's actually happening. It's traveling through the electric, and that's why the speed of the electric. That's why the speed of an electromagnetic wave is the speed of light. Because same thing. Anyway, now back to why this equation is the sine of. Let's do sine of x.
Yeah.
Okay. What's sine of x? Sine of x looks like this, right? What about sine of x plus b?
It's just going to be up.
Is it going to be right or left? Shifted right or left?
Okay. Yeah, to the left.
To the left, right? Because at negative phi, sine has to be 0. Right? When negative phi plus phi is 0, so sine of 0 is equal to 0. So this is going to be phi, right? And the same thing if we have sine of x minus phi.
Yeah.
We have, it's going to be the other side. Now let's go back to a general wave equation, one that we didn't really discuss. This is the same exact wave equation that we have. Multiplied by x plus or minus v. Well, v is c. C is speed of light. C times t. Okay. Let's just consider this part without this for now. Let's just consider sine of x plus or minus v of t or c of t. What is this? So this alone is a sine wave, right? This is the velocity, or the speed at which this entire sine wave is moving at. It's not the thing that's going up and down. It's the speed of this entire sine wave that's shifting.
Is it like the phase phi thing? Or?
Yes, this is exactly like phi. This is basically the phase.
Mm-hmm.
So as t increases,
Okay.
this is positive and increasing. If it's positive, remember when we have a positive angle, positive phase, it's to the left.
Yes.
As that quantity is increasing with time, phi is also increasing with time. Therefore, your wave is being shifted to the left.
Yeah.
If it's negative, then it's the opposite way around.
So the wave is traveling.
That's what?
So the wave is traveling.
The sine wave, yes. The sine wave is traveling. Sine wave is this thing
Okay.
is traveling.
Right.
So this is a function of two variables. The first variable is time. The wave is moving with time at a speed of c, which is the speed of light. X is the position along the axis that it's traveling. So at this position, at this certain time, it's going to have this much. And when we distribute this, so you can think of 2 pi over lambda as a scaling factor, because sine is kind of like, the units of sine is in radians, and the unit of this entire thing is in meters, right? So if you distribute this is k, 2 pi over lambda is k, you get the equation that we had in class, sine of kx, minus 2 pi over lambda c t. What's c over lambda? C over lambda?
Yeah.
C over lambda is equal to 1 over t0, where t0 is the period, because c is equal to lambda over t0. The speed is equal to, if this is for the black, this one, this is lambda, right? The length of the wave, which is length of the entire period, and the time it takes it to move from here to here. So the time it takes it to traverse this entire distance is time per period, which is t0. So distance traveled over time taken is equal to c, which is the speed. So that's why c over lambda is equal to 1 over t0. 1 over t0 is equal to f, frequency. 2 pi f is equal to omega, which is 2 pi f is equal to omega. So this entire quantity is omega. Kx minus omega t, which is the equation of the wave that we always use. That's how we got it. That's why we use it. That's why it makes sense. The negative, it moves to the positive direction because phase angle is decreasing. Negative phase is decreasing. Sorry, not negative phase. I mean, what I mean.
Yeah.
And that's why when it's positive, it's moving in the negative direction, and so on and so on. And this, I think, this is useful in one of the homework problems. I don't know if there might be a different one. In the first one?
I think we did this.
Did you?
Like that.
The original one? I don't know. Maybe I might be wrong. Don't quote me. But yeah, this is a nice form. It tells you more of what's going on, actually, instead of this one.
Actually, we already done that.
Thanks.
Mm-hmm. And I mean, C is equal to lambda f. That's the equation that we talked about in chemistry a very long time ago for any wave. Frequencies inversely related to the energy. Is directly related to the energy.
Do we have to know all these formulas?
Which one?
Like.
Some of those formulas are not on the
Yeah, they're not really on the sheet.
These aren't?
Some of them, just a couple, like a few of them.
Like what isn't?
I don't know, just like we'll be doing the homework and now realize that the equation that we
Yeah.
I mean, the important thing, like S equals E cross B, that's there.
Yeah, S equals E cross B direction. And the pointing vector, remember you can find the direction of the pointing vector based on this.
The spelling.
Well, that was a typo. I didn't realize that was actually a thing.
I don't know why they call it. Why they call it pointing?
There's a guy named Pointing.
Oh, really?
I guess, yeah. Like with a Y, Pointing.
Okay, so E cross B, right?
Huh?
E cross B.
Well, it depends on what
E?
yes.
Cross
Cross
B,
gives you
yes,
S.
Yeah. I still don't know very well example material.
What's up?
Very bad at that too.
What? Exam material?
Yeah, and the final exam is hard.
I'm just going to go to the final exam with all the first quantity in the cross product, all the second quantities in the cross product, now the third
I
quantity.
did that for the second exam, but he didn't ask much, like, of cross products, like relationships. Integrate you. I hate integration. Like, I just didn't, I don't know. I wrote down the formula, but I don't know how to integrate formulas.
Not really good enough.
Yo, what's your opinion about switching from chemistry to chemical engineering?
I'm not.
I know you're not.
No, I'm not.
You don't want to.
She was thinking about it.
I was thinking about switching to engineering, but apparently I'm not. No.
Why not? Why did you want to switch and why don't you want to?
I wanted to switch because